Video lecture on transportation problem, we shall discuss what is Vogel's approximation method. Initial basic feasible solution can be determined by several techniques like northwest corner method, row minima method, column minima method, matrix minima method, and Vogel's approximation method or VAM. So, what are the advantages of applying VAM over other methods on your transportation table? You should note that VAM gives us best IBFS. That means the results by other methods are equal to or inferior to that by VAM. How? That since our objective in a transportation problem is to minimize the total cost, VAM gives you the minimum cost among all these methods for finding IBFS. Although some people talk about degeneracy happening in VAM, you should note that degeneracy can happen, it can occur whenever the demand of any destination is exactly same as to the supply of an origin. So let us learn what is VAM. This is step 1. Next, this is step 2. Next, this is step 3. And next, this is step 4. Note those things quickly. I hope you have noted them. Therefore, let us learn how to find out initial basic feasible solution of this given transportation table by VAM. You should first check whether the model is balanced or not. You know that there is a necessary and sufficient condition for the existence of a feasible solution. What is the condition? The model should be balanced. That means the total supply should be exactly equal to the total demand. So what is the total supply to this problem? You may note that the total supply is 34 plus 15 plus 12 plus 19, that is 80, which is exactly equal to the total demand. Therefore, the problem is a balanced transportation problem. And to this balanced transportation problem, we apply VAM to find the initial basic feasible solution. Here you have 4 origins or 4 sources and 4 destinations. The supplies are also mentioned on the right side column and the demands are also placed in the bottom row. In first row, the minimum cost among these costs is 3 and the next minimum cost is 5. You find that you have 5 at 1 free cell as well as at 1 4 cell. However, you can take any one of these. What is the difference between the minimum cost and the next minimum cost? Clearly, the difference between 5 and 3 is 2. You call it your penalty. So, 2 is the penalty in the first row, that is first origin, and you place the penalty on the right side in a separate column and you usually put 2 within parentheses. In the second row, the minimum cost cell is 5 and the next minimum cost cell is also 5. You find that the difference between 5 and 5 is clearly 0. Therefore, 0 is the penalty along the second row. What about the third row? In the third row, the penalty is 1. In the fourth row, the penalty is 3. Next, you move to the columns. In the first column, the minimum cost cell is 5 and the next minimum cost cell is 6. The difference between them is 1. So the penalty along the first column or first destination is 1. You put 1 here in the bottom row and you put it in braces. Similarly, you determine the penalty of each and every row and column of your given transportation problem or transportation table. Next, what you do? You determine who is the maximum among all these penalties. You find that the maximum value among these penalties is 3 and these 3 occurs uniquely in this case in the fourth row. If there is a tie, what you should do? Okay, don't worry. We have already discussed one such case in this example as well. You shall learn it. Next, what you should do? You have determined the maximum penalty at this position. So along this row, you find out the least cost cell. Among these 4 cells, the least cost cell is 1. Okay, least cost cell is this cell with cost equal to 1. At this cell, the supply is 19, whereas the demand is 25. So how much you can allocate? The minimum of these two values, that is minimum of 19 and 25, that means 19. So you can allocate 19 at this cell. You can allocate it like this in the northwest corner in separate box. Remember, you have allocated 19, so you have nothing left along the fourth row, whereas you have 6 units left in the second column. You discard all other elements in the fourth row and move to next step. It has these 3 rows A, B, C and these 4 columns left with us. So it's a matrix of size 3 by 4. What about the penalties? Next set of penalties. So you have to draw another column on the right side of your copy, as well as you have to draw another row at the bottom of your copy. You find that in the first row, the least cost cell is 3 and the next least cost cell is 5. The difference between them is 2. So as before, 2 is the penalty in the first row. Similarly, you determine the penalties in each of these rows except the fourth row, because you have already consumed the supply of 19 and nothing is left here. So you have put a cross mark over that. In the first column, the least cost cell is 5 and the next least cost cell is not 6 but 7. Why not 6? Because you have already deleted that row completely. That element is not there in your transportation matrix. Therefore, what is the difference between minimum cost cell 5 and the next minimum cost cell 7? The difference is 2. You consider it as your penalty in the second stage. You put it within braces below. Next, you move to the next column. In this column, the least cost cell is 3 and the next least cost cell is 5. The difference between them is again 2. So you put 2 in this position at the bottom. Similarly, you compute all these penalties along these rows and these columns. You find that among all these penalties, the maximum penalty is 2, and that penalty 2 occurs in first column, second column, as well as in the first row. So it is a case of tie. You have to look for maximum allocations possible along these rows or columns. Let us start with the first column. In the first column, the minimum cost cell is 5. At 5, you can find that you have supply of 15 units and the demands of 21 units. Minimum of 15 and 21 is 15. So one can plan to allocate 15 units at this cell. Is not it? Next, what about the second column? In the second column, the least cost cell is 3. At 3, you have supply of 34 units and demands of 6 units. So you can allocate at most 6, because the minimum of 6 and 34 is 6 at this cell. Next, you move towards the first row. In the first row, with the same penalty 2, the minimum cost cell is 3. We have already noted that at 3, we can allocate at most 6 units. So, in which cell you can allocate the maximum amount? You find that you can allocate maximum amount at this cell along the first column with minimum cost 5. Therefore, what you should do? You should choose your first column. So we select the first column as this results in maximum allocation. Along this column, the minimum cost cell is 5. Minimum cost cell is this to one cell with cost equal to 5. How much do you allocate? We have already noted that we should allocate 15 at this cell. Therefore, we have already consumed all the supplies available along row 2. We delete the rest of the elements in this row. We also adjust the demand that you have at destination 1. From demand of 21, we have already sourced 15. So the left out is 6 units of demand for destination 1. This is about step 2, and let us now move to step 3. In step 3, we have this transportation table with us. In this table, we have already deleted the second row and the fourth row. Therefore, we are left with A and C rows, or origin A and origin C, along with these four columns. So in these 2 by 4 matrix, you compute the penalties as before. You find that the penalties are along the first row 2, along the third row it is 1, along the first column it is 1. How? Along the first column. You find that along the first column the minimum cost cell is 7 and the next minimum cost cell is 8. Don't consider this either 5 or 6 because you have discarded them. So the difference between this 7 and 8 is 1, and you put 1 within braces as your third set of penalties. Next, here it is 3, it is 1, and along the fourth destination the penalty is 0 because the difference between 5 and 5 is 0 clearly. Okay, so who is the maximum? Among all these penalties in all these rows and columns, you find that the maximum penalty is 3 and it occurs along the second column. So in this column, who is the minimum cost cell? You find that 3 is the minimum cost cell. What is the cost? How much can you allocate at this cell? You find that in this cell, the minimum of 6 and 34, that is 6 units, can be allocated. Cross out rest of the elements in this second destination as we have already covered all these demands. However, we are left with 34 minus 6, that is 28 units of supply along the first row. Find that there are 2 rows left and 3 columns left. So this table is a 2 by 3 table. In this transportation table, we compute the penalties as before. In the first row, the minimum cost cell is 5 and the next minimum cost cell is 5 because these two cells have the same cost. Therefore, the associated penalty is the difference between them, which is 0, and hence we write the penalty as 0. We move to the third cell row. In the third row, the minimum cost cell is 5 and the next minimum cost cell is 6. The difference between them is 1. Therefore, 1 is the penalty for the third row in this route. Next, we move into the columns. In the first column, the minimum cost cell among 7 and 8, that is these two cells, is 7 and the next minimum cost cell is clearly 8. So the penalty in this column is 1. We put the penalty in parentheses below as our fourth penalty. Rest of the penalties we can compute similarly. Among all these penalties, we find that maximum penalty is 1 and this 1 occurs in the third row, in the first column as well as in the third column. So which column or row do you want to choose? You do that based on maximum possible allocation. So let us start with the third row. In the third row, the minimum cost cell is 5. At this cell, supply is 12, the demand is 17, the minimum of them is 12. Therefore, you can allocate 12 units at this cell. If you choose your first column, at the minimum cost cell is 7, and at this cell, how much can you allocate? At this cell, the supply is 28 and the demand is 6. Therefore, you can allocate at most 6 units to this cell. Next, you find that if you choose your third column, at this column, the minimum cost cell is 5 and at this cell, you can allocate the minimum of 17 and 28, that is the minimum of the demand 17 and supply 28, which is 17. Now, among these three values of 6 at 1 position, 17 at 1 position and 12 at 3 position, you find that 17 is maximum and you find 17 occurs along the third column. Then that the minimum cost cell is 5 and at this cell you allocate 17 units as before. Therefore, you cross out the rest of the elements of this column and you adjust from your supply in the first row. The supply was 28, you have allocated 17, so you are left with 11 units of supply along your first row. So let us move towards step 5. In this case, we are left with a 2 by 2 matrix where we are left with 2 rows A and C and 2 columns 1 and 4. Therefore, in this 2 by 2 matrix with cell having cost 7, 5, 8 and 5, you compute the penalties as before. The fifth set of penalty gives you 2 and 3 along this first and third rows respectively, and 1 and 0 along the first and the fourth column respectively. What about the maximum of these penalties? You find that the maximum of these penalties is 3 and this occurs along the third row. So you select the third. What about the minimum cost cell in the third row? You find that the minimum cost cell is 5. How much do you allocate there? You can allocate the minimum of the supply and demand, that is minimum of 12 supply and demand 17, which is 12. Therefore, if you allocate 12 units at this place, you have consumed all the supplies available from origin 3 or third origin. Therefore, you cross it out and you also adjust your demand for the fourth destination. Since you had 17 units of demand at this destination 4 and you have already covered 12 units of demand through your third origin, therefore you are left with 5 units of demand for the fourth destination. Next, we move to the next step. In this step, we find that we are left with only a matrix of size 1 row and 2 column. Therefore, how do you compute the penalties? As before, you find that the penalty in the first row is the difference between 7 and 5, which is 2. In the first column, the penalty is clearly the difference between this 7 and the next cost cell. Since there is only one cell along this column, so this value is itself the penalty. So the penalty along this column is 7. Similarly, along the fourth column, since there is only one cell available, therefore the penalty along the fourth column is also 5. What about the maximum of these penalties? You find that the maximum of these penalties is 7. Therefore, you allocate a maximum amount at this cell. What is the maximum amount? The maximum amount was 6. So we have allocated 6 units at this cell. If you allocate 6, you find that you are left with 5 units of supply in the first row as well as 5 units of demand at the fourth column. Therefore, you allocate 5 at the remaining cell of this table, like this. You observe that no supply or no demand is left out to this balanced transportation problem. Next, you compute the total cost. How do you determine the total cost in your initial basic feasible solution? You multiply this amount by corresponding cost. I hope you can recall that if this 6 means you transfer 6 units from origin A to destination 1, but the per unit transportation cost is 7. Therefore, this cell cost you 6 into 7 units. Similarly, this cell cost you 6 into 3 units. This cell 17 into 5 units. This cell 5 into 5 units. This cell 15 into 5 units. This cell 12 into 5 units. This cell 19 into 1 units. So the total cost is therefore 324 units. You observe that 1, 2, 3, 4, 5, 6 and 7 occupied cells with positive allocations are there in your initial basic feasible solution. This completes the VAM process and the method is thus complete. Next, you have to improve on your initial basic feasible solution if possible and thereby determine the optimal solution by modified distribution method or stepping stone algorithm. So dear friends, we present all these methods like northwest corner method, matrix minima method and Vogel's approximation method in separate videos. We illustrate 3 examples in all these videos. You can find them in the description section. You can find the link there. Not only that, we have also discussed what is MODI method or modified distribution method or UV method for determining the optimal solution from the present IBFS in separate videos. You can find another video where you consider a very complicated example in which the transportation problem is not balanced. The initial basic feasible solution that you generate through VAM is also degenerate. And not only that, you need to form a loop for determining the optimal solution.